In August 1939, just days before the outbreak of the Second World War, a small German aircraft took to the skies over Rostock. It bore no armament, no camouflage, and no propeller. In 6 minutes of flight, it demonstrated a revolutionary technology that would change aviation forever. This is the story of the Heinkel He 178, the world's first jet-powered aircraft. Oh, that's right, we are at last covering the jet age. An age of speed, high altitude, and unrelenting progress. It began as a technological revolution that made the rapid advances of the interwar years seem almost pedestrian in comparison. In 1943, the fastest operational fighters in the world were piston-engined thoroughbreds. The North American P-51B Mustang could reach around 440 miles an hour at altitude, the Supermarine Spitfire Mark IX topped out near 410, and the German Focke-Wulf FW-190A5 was among the fastest in the Luftwaffe's inventory at just over 400, or for metric 642 kph. For all their power, though, none could sustain speeds far beyond this, and breaking through the 450 mph barrier in level flight was still a distant goal. Yet, just 10 years later in 1953, the jet age had completely rewritten these numbers. The English electric Canberra, a bomber, mind you, could cruise at 480 miles per hour. The MiG-17 and Hawker Hunter pushed past 600 miles an hour in level flight, and at the cutting edge, the North American F-100 Super Sabre had entered service as the first production fighter capable of supersonic speed in level flight, twice as fast as the best fighters from 1943. Without even touching on the advances in avionics, weapons, and infrastructure that had to evolve just to keep pace, the arrival of the jet engine collapsed and eclipsed decades of incremental progress into a single breathtaking leap. In barely 10 years, jets pushed speeds, altitudes, and climb rates so far beyond piston-era limits that everything had to change. Runways stretched into miles of concrete. Gun sights had to be guided by radar, cockpits were sealed and pressurized against the thin air of 50,000 feet, and wings were swept back like arrows to slice through the sound barrier. To give you another bit of perspective on the insane pace of jet aircraft development, just 25 years separate the maiden flights of the world's first jet-powered aircraft and the world's fastest jet-powered aircraft, the SR-71 Blackbird. Which allows for a delightful segue to talk about a Blackbird-themed watch thanks to REC Watches, today's sponsor, and their Habu series, a timepiece that doesn't just take inspiration from the Blackbird, but actually contains metal from the iconic aircraft itself. REC watches are well known for incorporating real pieces of history into their timepieces, and this one is no different. The Habu incorporates genuine titanium from Blackbird number 61-7956, the most flown SR-71 in history with over 1,450 missions and nearly 4,000 hours in the air. That's equivalent to flying around the world more than 160 times at 3 times the speed of sound. This particular Blackbird served at Kadena Air Base in Okinawa, where the aircraft stationed there earned the nickname of Habu after the local pit viper, a name that now lives on in this limited edition watch. The lower dial contains titanium sourced from the aircraft's inner engine nacelle exhaust ejectors, the so-called turkey feathers that regulated the Blackbird's mighty afterburners. These components were provided by Daniel Freeman, former supervisor and chief of metals technology for the 9th Reconnaissance Wing, who was directly involved in the SR-71 program. The rest of the design draws directly from the SR-71's form and function. A titanium case for strength and lightness, cockpit-inspired gauges, brushed hands shaped like the Blackbird's silhouette, a crown and guard shaped after the SR-71's distinct engine inlet cones, and a Kevlar-inlaid FKM rubber strap with nice red no-step stripes. It is a truly gorgeous, well-made, and captivating watch, and I can attest to the build quality as someone who has had a REC watch on his wrist for several years now, and the Habu is available to purchase exclusively at recwatches.com. Of course, this is the part where I tell you, my dear viewers, of the wondrous benefits of supporting me, because if you click on the link in the description below and use the code REX, you'll get a 10% discount off your purchase. So thank you to REC Watches for sponsoring today's video. And now, where was I? Oh yes, the dawn of the jet age, a technological revolution, blah blah blah. But every revolution has its beginning, and for the jet age, it began with the Heinkel He 178. Now, of course, in reality, this is a gross oversimplification. The dawning of the jet age was the product of decades of theoretical work conducted by many gifted individuals, often resulting in parallel breakthroughs. It's a deeply complex topic with many conflicting stories, depending on what sources you read, and one that deserves exploring in real depth. But for the purpose of this video, I am going to condense this into a few short paragraphs so that I can actually focus on the aircraft itself and its engine. Another, much longer video on jet engine development in general will come later, heaven help me. So, let's set the scene a little bit. By the 1920s and 1930s, aviation had advanced at a staggering pace. The all-metal monoplane had replaced the fragile biplane, retractable landing gears and streamlined cabins were becoming standard, and piston engines were more powerful than ever. Aircraft like the Supermarine Spitfire and the Messerschmitt Bf-109 could now exceed 350 miles per hour, speeds that, only a decade earlier, would have been considered the realm of daredevils or liars. But as these speeds increased, engineers began to encounter a fundamental barrier. And that was propeller tip speed. You see, the outer ends of a propeller blade travel much faster than at the center near the hub, and as airspeed and rotational speed increase, the tips approach the speed of sound. Near this threshold, shockwaves form, causing sharp drops in efficiency, severe vibration, and mechanical stresses. Now, this wasn't an absolute engineering brick wall, but beyond this point, squeezing out more speed became an exercise in diminishing returns, and side effects. One of those side effects was noise. A lot of noise. Supersonic propeller tips would essentially generate a constant series of small sonic booms, hundreds of times per second. Later on, this would be demonstrated, enthusiastically demonstrated, by the Republic XF-84H Thunder Screech in the 1950s. Perhaps the most accurately named aircraft in existence, it tried to operate with propeller tips that rotated at Mach 1.18, or 1,446 kilometers per hour. It became infamous for being so loud that it could be heard from dozens of miles away. Ground crews reported nausea, headaches, seizures, and a strong desire to be somewhere else, and test pilots refused to fly it. Now, that is of course an interesting and somewhat entertaining topic that we will come to in another video. But, back to the 30s. This physical limit, combined with the impracticality of brute forcing around it, made alternative propulsion methods attractive to forward-thinking engineers. Now, the gas turbine, long studied in stationary applications, offered a possible solution. The principle of a gas turbine engine is simple in theory. Air is drawn in, compressed, mixed with fuel, combusted, and expelled at high velocity to produce thrust. It was not a new theory, and it had existed on paper in one crude form or another for years. But in practice, building a lightweight, reliable turbine engine capable of continuous high-power operation was a monumental challenge. The obstacles were many, and they were inconveniently interconnected, as in solving one problem usually required solving three. Metallurgy, for example, was not yet producing alloys that could safely cope with the environment found inside a jet engine. Turbine blades in these early designs faced prolonged exposure to combustion temperatures exceeding 700 degrees Celsius, conditions few engineers had ever needed to consider before. The alloys of the time had been developed for piston engines, steam turbines, or other far less punishing applications, and they tended to treat these new temperature ranges as a polite invitation to soften, warp, or fail outright. Precision manufacturing was another challenge to overcome. Compressors and turbines, spinning at tens of thousands of revolutions per minute, didn't take kindly to the sort of imperfections that were still common in the machine shops of the day. Even a minor flaw in a blade could lead to imbalance, vibration, or in the worst cases, a very expensive shrapnel factory. Aerodynamic knowledge of compressor and turbine stages was also incomplete, which meant that early designers spent a lot of time trying to avoid surging or stalling in the compressor. These were professional engineering terms for, "We'd like the engine to stop exploding, please." And since weight and compactness were essential for anything that had to leave the ground, designers couldn't simply shrink a stationary industrial turbine and bolt it to a wing. They had to invent entirely new layouts, bearings, and cooling systems from scratch. So, as I said, the challenge was monumental, but scientists and engineers persevered, and towards the middle of the interwar period, a few individuals were making real progress. Today, we're just going to focus on two, because they are the most relevant to this video's topic. In Britain, Frank Whittle, an RAF officer with a knack for unconventional thinking, began working on a jet propulsion concept in the late 1920s. He opted for a single-stage centrifugal compressor, a design well understood from superchargers, paired with multiple external combustion chambers feeding into a single axial turbine. This configuration was mechanically sound, compatible with the manufacturing tolerances of the day, and robust enough to survive more than one test run. Unfortunately, Whittle struggled to gain official support, but that didn't stop him. Whittle founded Powerjets Limited in 1936. With minimal funding, he and a small team began bench testing experimental engines. The first prototypes suffered the usual early engine ailments: bearings that wore out, metals that softened, and a general reluctance to run for very long. But in April of 1937, the WU, also known as the Whittle unit, finally ran for sustained periods. For a machine entirely dependent on untested ideas and fragile metallurgy, that on itself was a small miracle. Meanwhile, across the Channel and a few hundred miles away in Germany, Hans von Ohain, a physics student at the University of Göttingen, was working independently on his own turbojet concept. His designs combined an axial inducer stage, a short set of blades at the front that straightened and smoothed the incoming air, with a centrifugal compressor. This hybrid arrangement gave a smoother airflow into the compressor than a pure centrifugal layout, and allowed the engine to be more compact in length than a purely axial design, though at the cost of some ducting complexity. Von Ohain's earliest experiments used hydrogen as fuel. This wasn't because he had visions of a future hydrogen economy, but because hydrogen burns cleanly and ignites easily, making it ideal for bench testing. It avoided producing carbon deposits and soot buildup, and it simplified the sealing challenges when working with early alloys and lubricants. In 1934, lacking any sort of industrial backing, he partnered with Max Hahn, a local car mechanic who had the skills and the tools to turn Ohain's sketches into crude but functional test rigs. Now, it's important to briefly address something that comes up a lot when discussing early jet engine development. Did Ohain nick Whittle's ideas? In some circles, it's claimed that Ohain had read Whittle's 1930 patent for his turbojet and used it as a stepping stone for his own work. The truth is different, and a bit more nuanced. Before filing his own patent in 1935, von Ohain's attorney uncovered Whittle's earlier patent. Now, to avoid a potential legal headache, he advised narrowing certain claims so that they wouldn't overlap with Whittle's. Von Ohain later acknowledged that he had reviewed Whittle's patent at that time, but insisted that his own core concepts, including the axial centrifugal layout, were already in his notebooks before he even became aware of Whittle's work. Whittle, for his part, had initially suspected that von Ohain's design was a derivative of his own, but post-war technical comparisons convinced both men that these were genuinely different engineering solutions to the same problem, a rare case of true simultaneous invention. Now, getting back to the engine itself, these early experiments caught the attention of von Ohain's professor, Robert Pohl, in 1936. Pohl then introduced him to one Ernst Heinkel, one of Germany's most ambitious aircraft manufacturers, and this is where the story of the Heinkel 178 truly begins. By the mid-1930s, Ernst Heinkel had established himself as one of Germany's most prominent aircraft manufacturers. His company, Heinkel Flugzeugwerk, produced a range of military and civilian aircraft, from fast reconnaissance planes to advanced bombers. But Heinkel was not content to simply meet the requirements of the Reich Luftwaffenministerium, or the Reich Air Ministry, or RLM for short. He was a forward-thinking man, always looking for the next leap in aviation technology, and he was not especially patient about waiting for official permission to take it either. Heinkel had a history of backing unconventional projects, and his newest passion was the exploration of high-speed powered flight. Thus, when Hans von Ohain and Max Hahn presented Heinkel with the concept of a practical turbojet, he recognized the potential immediately. Heinkel agreed to support the project, not under any official Luftwaffe or RLM sanction, but as a private and secret development program. This was not Heinkel's only covert venture. Around the same time, he also authorized the construction of the world's first liquid-fueled rocket aircraft, developed in collaboration with a young rocket engineer named Werner von Braun. The rocket plane would be designated the Heinkel 176, and the turbojet project became the Heinkel 178. Both were experimental machines unlike anything else in existence in Germany, each requiring entirely new engineering approaches, new materials, and new operational procedures. Neither was likely to see service anytime soon, as a practical design, but Heinkel wasn't aiming for immediate practicality. He was aiming to prove what was possible, even if it meant operating at the very edge of what his engineers and the technology of the day could handle, and even if it meant doing it behind the back of his own government. The Heinkel HE-178 was designed by Siegfried and Walter Gunther, Heinkel's chief designers, along with Heinrich Hertel. Tragically, Walter Gunther died in a car accident in 1937, but Siegfried carried on with the work. The Heinkel 178 was an airframe built to test the new jet engine and nothing else. It was not intended to be any sort of production aircraft, and as such, the design team made deliberate compromises in the pursuit of three distinct goals: simplicity, lightness, and engine accommodation. It had straight, tapered wings mounted high on the fuselage, with a small amount of dihedral. These wooden wings were designed by the Gunther brothers and used an airfoil that was 12% thick at the root, tapering to 7% at the tips. Large trailing edge flaps were placed inboard, with the ailerons on the outer sections. The tailplane and elevators were also made of wood. No attempt was made to incorporate swept wings, as aerodynamic research in this area was still developing, and it was unnecessary for proof-of-concept flights. The only concession to complexity was the landing gear. Designers initially planned for all three wheels to retract into the fuselage, as speeds of over 800 km an hour were hoped for. But during the first flights, the gear was to be left fixed in place with the retraction openings fared over, and, as it turned out, this would be the only configuration that it was ever operated in. As a test aircraft, the Heinkel 178 had just a single cockpit, which was positioned well forward of the wing leading edge, with its canopy smoothly fared into the dorsal spine. Directly behind the cockpit sat a single fuel tank, followed by the jet engine, whose intake was roughly level with the wing's trailing edge. Air entered through a simple circular nose intake, then flowed along a duct that curved under the cockpit and the fuel tank before reaching the engine. Exhaust gases exited through a long tailpipe, nearly a third of the aircraft's total length, and out the rear fuselage. Side intakes were considered during the design phase, but were ultimately rejected in favor of the more simple nose intake. The jet engine itself, of course, was the main feature, and at this point it was the product of 2 years' painstaking and remarkably rapid work. While across the channel, Frank Whittle struggled to find financial and government support for his own endeavours, which in hindsight, the story of which is a topic for another day and one of pure insanity, Ohain now enjoyed the patronage of a major German industrialist, and this quickly bore fruit. In 1936, Heinkel brought von Ohain and Hahn into his company and set up a small and dedicated research division at Heinkel's factory. This was located in the suburb of Marienea in Rostock. The arrangement gave von Ohain access to skilled craftsmen, advanced materials, and wind tunnel facilities, resources he could never have dreamed to acquire on his own. The result was that by September 1937, less than 12 months later, von Ohain's first experimental engine, the HES-1, had run successfully on hydrogen. Built largely from sheet metal, it featured a two-stage compressor, an axial stage followed by a centrifugal radial impeller, feeding an annular combustion chamber which drove a single-stage radial turbine. Though the HES-1 wasn't intended for flight, this proof of concept was critical as it validated the core idea of sustained turbojet operations. While work on the HES-1 continued, Ohain's team started work on a new petrol-fueled turbojet, the HES-3, and this was to be the power plant for the Heinkel 178 prototype. Now, this engine was a good example of von Ohain's preference for compactness over sheer power, something that influenced much of his early work. Unlike Frank Whittle's straight-through designs, the HES-3 used a reverse-flow annular combustion chamber. After compression, air was routed forward around the combustor casing, then reversed to flow aft into the turbine. This arrangement allowed for a shorter overall engine length, though it did introduce some additional ducting losses, but for von Ohain this was considered acceptable. Bench tests of the first HES-3, which later became known as the HES-3A, began in March 1938, and the results were underwhelming at first. It was meant to produce 1,760 pounds of thrust, but it barely managed half of that. Less of a jet engine and more of an expensive way to heat the workshop at this point. The main issue was that the compressor and the combustor were kept small to reduce the frontal area, which limited airflow and, in turn, the thrust. The design was later revised into the larger HES-3B, which came close to producing 1,000 pounds of thrust, but the HES-3A still had its uses for airborne tests. Flight testing of the first engine began in mid-1939. Now, some sources say May, others say July, but it happened around this period. The engine was mounted beneath a Heinkel He-118, registered DOVIE. This particular aircraft had lost out to the Junkers Ju-87 Stuka in the Luftwaffe's dive bombing competition, but it proved perfect as an early jet engine testbed. These were the first ever flight trials of a turbojet engine, and they were carried out under strict secrecy. Takeoffs happened before sunrise, sometimes as early as 4 o'clock in the morning, and landings were made before the factory opened for the day. For both takeoff and landing, the He-118 used its piston engine, and the turbojet remained shut down until the aircraft was fully airborne. The Heinkel 118 was ideal for the role because it was a two-seater and it had long landing gear legs, giving ample clearance for the jet unit to be mounted under the fuselage. Heinkel's chief test pilot, Erich Varsitz, flew every mission, with company flight engineer Walter Kunzel seated behind him. It was Walter's job to start and then monitor the jet engine during flight. The flight test was a resounding success. Ernst Heinkel later described that first ignition. As the turbine lit, a bluish jet plume shot out, and almost immediately the aircraft surged forward to an astonishing speed. Several other flights followed after this without incident, until, in the finest tradition of experimental engines, the HES-3A caught fire and destroyed itself after landing. At least it had the decency to wait until the plane was safely on the ground. Even so, the tests had yielded valuable performance data, and the improved HES-3B was now ready to be installed in the completed HE-178 airframe. The changes from the original HES-3 to the 3B included redesigned curved guide vanes between the compressor and combustion chamber and at the turbine inlet. The HES-3B featured a 14-blade axial inducer, a 16-blade centrifugal compressor, and a 12-blade radial inflow turbine, and it could operate on either petrol or diesel fuel. By the summer of 1939, the HE-178 prototype, known as the V1, was complete and ready for taxi trials. The HES-3B engine had been mounted into the fuselage and connected to its ducting system. Engineers knew that they were about to attempt something that no one had done before: fly an aircraft entirely under turbojet power. At this point in its development, the HES-3B was far from being a reliable flight engine. Even so, Ernst Heinkel was eager to get the Heinkel 178 airborne as quickly as possible. Von Ohain's confidence in the engine was restrained, but apparently restrained was good enough and sufficient to proceed. After all, no milestone in aviation was rarely achieved by waiting until everything was perfectly safe. Despite this, a high degree of caution was still paramount. No one knew exactly how the aircraft would handle the unique thrust characteristics of a jet, particularly during takeoff and landing. Secrecy was also paramount. The Reich ministry was not informed of the HE-178's existence during its design or construction phase. Only a select group of engineers and technicians within Heinkel itself knew the full scope of the program. Even within the factory, parts of the aircraft were built in different workshops to minimize the number of workers who could piece together what was happening. Heinkel knew that official involvement would have brought with it the joys of bureaucracy, delays, forms, and the very real prospect of the entire thing being strangled in its cradle by more sensible projects. Hermann Göring, as Reichsmarshal to the RLM, was primarily focused on rapid rearmament with proven designs for the war that he knew was coming. This meant fighters, bombers, and support aircraft that could be mass-produced immediately. Now, that's not to say that he wasn't aware of jet technology development, but Göring was not personally a technical innovator. He tended to rely on subordinates like Ernst Udet, responsible for Luftwaffe procurement, to filter and select projects if they showed promise. Göring's stance towards jets was more one of passive awareness rather than active enthusiasm. If the RLM saw potential, he'd sign off on it, but he wasn't actively seeking out its advancement. Now, by 1939, Ernst Heinkel almost certainly would have known, or at least very strongly suspected, that war was imminent, and that awareness also likely influenced his decision to keep the Heinkel 178 a secret project. He reasoned that a flying prototype would be far more persuasive to the Reich ministry than yet another set of drawings. And so, it was that Germany was about to attempt the world's first jet-powered flight, a propaganda coup in the waiting if there ever was one, while its own leaders remained blissfully unaware. Taxi runs were conducted on the 14th of August 1939, with Chief Test Pilot Erich Vossitz at the controls. The sessions revealed two important traits. The HES-3B engine gave exceptionally smooth power delivery in comparison to piston engines. Instead of the vibration and torque pulses from reciprocating cylinders, its turbojet produced a steady stream of thrust, with only minor high-frequency vibrations from the compressor and turbine. The other trait was a sluggish throttle response. Throttle control was directly linked to fuel flow, with response times being slower than piston engines due to the turbojets needing to spool up. This was one of the first practical lessons that test pilots would learn about jet propulsion, and it was a characteristic that would remain a real challenge in early jet aircraft designs. During a high-speed taxi test on the 24th of August, Vossitz unintentionally achieved the first airborne moment in a jet-powered aircraft. As he accelerated along the runway, the Heinkel 178 gained lift at around 130 km an hour and briefly became airborne before being set back down. The first official flight came 3 days later, in the early morning of August the 27th. Before the historic maiden flight, Vossitz was cautioned not to push the airframe too hard. The fixed landing gear created a lot of drag, so high speed was out of the question anyway, and the HES-3B was only cleared for 6 minutes of operation, and no one was entirely sure what would happen if he stayed up much longer than that. In other words, history's first jet-powered flight was scheduled to be little more than 2 gentle laps around the airfield. Even within that modest envelope, drama managed to unfold. After an unremarkable takeoff and flight, near the end of the second circuit, a fuel pump failed. Fortunately, the engine kept running well enough for Vossitz to make an approach for landing. Wanting to get down quickly, with the engine failing, Vossitz executed a side-slip, an unusual and daring maneuver on the very first flight of a completely new aircraft with a completely unproven power plant, but needs must. As he lined up to land, another challenge appeared. The low early morning sun was glaring off a mist that clung to the airfield, making the runway almost impossible to see. Later on, Vossitz would simply call the visibility terrible. Even so, Vossitz brought the Heinkel 178 down for a smooth landing, ending the world's first flight of a turbojet-powered aircraft. The flight had lasted only 6 minutes, but it marked the beginning of a new era in aviation. To celebrate, Vossitz, von Ohain, Heinkel, and other members of the team had a champagne breakfast immediately afterwards at the airfield. From this very first flight of the Heinkel 178, several important impressions were recorded. The HES-3B turbojet produced a high-pitched whine, almost a howl, unlike anything heard from piston-engine aircraft with their deeper, throaty roars. Within the short, cautious flight profile, the controls had felt normal and stable, and no handling problems had been reported, though more extensive, higher-speed trials would have been needed to judge stability completely. Engineers noted that the long tailpipe ran extremely hot during operation, raising concerns about possible heat damage to the rear fuselage if the engine were to be run for extended periods of time. And, on landing, the aircraft behaved much like other jets that were to come, with a noticeably longer rollout than comparable propeller-driven types, a result of the lack of propeller drag combined with a relatively high approach speed. Taken together, these findings reassured Heinkel that the 178 was at least a credible proof of concept, if not yet a fully practical aircraft. 2 weeks later, Germany was at war, and Heinkel decided it was time to reveal the existence of the 178 to the Reich Air Ministry. On the 1st of November 1939, senior officials, including General Oberst Ernst Udet and General Erhard Milch, were invited to Marienwehr Airfield for a demonstration. Exactly how many times the Heinkel 178 had flown before its presentation to the Reich Air Ministry is a matter for debate among historians. The book Jet Prototypes on World War II states that the second flight was the demonstration for senior Luftwaffe officials, implying only one prior test, which was the maiden flight on August the 27th. But other respected sources, including Ernst Heinkel's own memoirs, Dan Sharp's research, and William Green's Warplanes of the Third Reich, describe several short proving flights in the days and weeks before the RLM visit. In these accounts, Heinkel kept the jet strictly within company hands, fine-tuning its performance and ironing out any teething issues before risking a public showing. Now, I'm inclined to believe that several more flights would have been conducted before showing the prototype to Air Ministry officials. Having its second flight as a public demonstration would have been a huge risk, and as it happened, the demonstration itself was not without a bit of drama. The first attempt at takeoff ended prematurely when the engine failed to reach full thrust. Engineers quickly corrected the issue, and on the second attempt, Vossitz took off and performed several passes over the airfield, including a bit of low-level buzzing of the distinguished visitors. This may have been intended to impress them, but surprisingly, Vossitz received the contrary reaction. To Heinkel's shock and bitter disappointment, the RLM's reaction to the 178 appeared to be lukewarm at best. Ernst Udet is often quoted as calling the Heinkel 178 an interesting toy, reflecting the prevailing view that such aircraft were not immediately relevant to Germany's war plans. The Luftwaffe's leadership, especially under Udet and Milch, were focused on building large numbers of proven piston-engine fighters and bombers, rather than diverting resources into experimental projects. Piston engines were already delivering excellent performance. The Messerschmitt Bf-109 was fully competitive with Allied fighters, and the new Focke-Wulf 190 prototype was showing great promise. By contrast, jet engines were unproven in combat, their endurance and reliability were questionable, and their manufacturing feasibility was completely uncertain. Germany's aircraft industry was already stretched to the limit producing aircraft of conventional design in quantity. In this climate, a small, single prototype jet, however innovative, could not compete for attention with mass-producing designs that could be deployed immediately to the front lines. But, and as I like to say, this is a big, curvaceous but, while the public reaction was dismissive, the demonstration had a stronger impact inside the RLM's technical branch. Once the report of the 178 landed on the desk of Dr. Hans Marsch, head of the Aero Engine Development Department, it became clear that turbojet propulsion was no longer just a theoretical curiosity. Working with his deputy, Helmut Schelp, Marsch began quietly increasing resource allocations for jet engine development. However, the bulk of this funding went not to Heinkel and von Ohain's centrifugal engines, but to Junkers and BMW, both of which were working on axial flow turbojets, the Junkers UMO 004 and the BMW 003. These promised higher thrust and a more compact installation. Part of the reason that Heinkel was sidelined was structural. The RLM generally preferred to keep airframe builders and engine manufacturers as separate entities, avoiding overlap and competition for resources. Now, Junkers was the major exception. In 1936, the German government had merged its aircraft and engine divisions into Junkers Flugzeug und Motorwerk AG, and by 1939 the company was by then recognized as one of Germany's largest industrial concerns. Crucially, this was all done with official sanction. By contrast, Heinkel's jet program, with both engine and airframe development entirely in-house and without RLM oversight, was an unsanctioned anomaly. To the ministry, it looked like duplication at best and freelancing at worst. Now, there was also an undeniable political dimension. Messerschmitt AG, led by Willy Messerschmitt, had close ties to RLM officials, and it had already supplied the Luftwaffe's frontline fighter, the Bf 109. Even when Heinkel unveiled the more advanced Heinkel 280, the world's first twin-jet fighter, the RLM ultimately channeled resources towards the Messerschmitt Me 262. Commonality with existing production lines, pilot familiarity with Messerschmitt cockpits, and Willy Messerschmitt's political capital with the Nazi Party all worked in his favour. Heinkel had not always seen eye to eye with his fellows in government, and additionally, the secrecy that had allowed Heinkel to design and build the 178 without bureaucratic interference also had its after effects. Because the RLM had not been involved in commissioning, funding, or supervising the project, they had no institutional investment in its success. When the aircraft was revealed, it was viewed as a private experiment rather than an integral part of Germany's official jet development program. For the RLM, the logic was straightforward. They were more inclined to back projects that they had initiated and could control from the outset. The Heinkel 178 may have been the first to fly, but in official eyes it was a side branch of development. Interesting, but outside the main flow of wartime priorities. Determined not to be left behind, Heinkel initiated the aforementioned HE-280 project in late 1939, even before the RLM had officially acknowledged the existence of the Heinkel 178. Now, if the 178 was a polite proof of concept, the 280 was to be a full-throated attempt to show the Luftwaffe what a jet aircraft could really do. It became the world's first twin-jet-powered fighter prototype to fly under its own power, achieving this milestone in April 1941, a full 15 months before the maiden flight of the Messerschmitt 262 under jet power. It incorporated several lessons learned from the Heinkel 178, including the adoption of a cleaner aerodynamic design with shorter exhaust ducts to minimize thrust loss, and an airframe intended for higher thrust engines, beginning with Heinkel's own HES-8 and later considering the BMW 003. In flight trials, the Heinkel 280 demonstrated impressive performance for its time, and it was capable of outpacing early prototypes of the Messerschmitt 262. However, by 1943, the RLM made the political and strategic decision to abandon the Heinkel 280 in favour of the Messerschmitt 262. This choice was driven by a few factors. Messerschmitt could adapt existing fighter production facilities to manufacture the 262, whereas Heinkel had more of a bombing focus. The B&W 003 engine intended for the Heinkel 280 was delayed, while the more mature Junkers Jumo 004 was already committed to the Messerschmitt 262 program. I'll go into more details on that in a separate video on the Heinkel 280, but needless to say, it was a dead end. As for the Heinkel 178 itself, its flying career was short and unspectacular. The prototype that made the historic first flight of a jet aircraft flew only a handful of times after the RLM demonstration before being retired as a static display piece. It was later placed in the Berlin Air Museum, where it might have enjoyed a dignified old age had it not been for an Allied air raid in 1943 that destroyed both the museum and the world's first jet-powered aircraft. A second airframe, the Heinkel 178 V2, was under construction, with refinements such as retractable landing gears, a tidier canopy, and plans for the more powerful HES-6 engine, but as Heinkel's attention shifted to the Heinkel 280, work on the V2 was slowed down and then eventually abandoned. In historical terms, the Heinkel 178's influence was subtle but significant. It did not lead to production orders or frontline service aircraft, but it served as tangible proof that jet propulsion was not only possible, but practical. The RLM's engineers, particularly Hans Mausch and Helmut Schelp, took the lessons to heart, even if they did choose to develop the concept through other manufacturers. The Heinkel 178's true legacy lay in triggering the acceleration of Germany's jet engine programs. For Ernst Heinkel, however, the story was bittersweet. His company had been the first in the world to fly a turbojet aircraft, yet the glory and the production contracts would go elsewhere. When Germany's jet technology became known to the Allies in 1945, the Heinkel 178 was retrospectively recognized as a milestone achievement. The surviving documentation, photographs, and film footage, of which there is a bit available, confirmed that Germany had achieved jet-powered flight nearly 2 years before Britain's with the Gloster E-28/39. Post-war interviews with Hans von Ohain and Ernst Heinkel confirmed that the project had been developed entirely in private, without RLM involvement until after the first flight. Allied engineers studying the Heinkel 178 remarked on its simplicity, a small wood and metal airframe wrapped around a compact centrifugal turbojet. Compared to the temperamental and maintenance-hungry monsters that would follow, hello Messerschmitt 262, it was almost elegant. Hans von Ohain himself emigrated to the United States in 1947 under Operation Paperclip, joining the US Air Force's Wright-Patterson Air Base as a research scientist. There, he contributed to gas turbine advancements, ramjet studies, and combined cycle propulsion concepts. Or, in other words, he went from the humble beginnings of let's try to make a jet engine work to let's see how fast we can melt the test stand this week. Nearly 20 years later, in 1966, von Ohain would meet Frank Whittle for the first time at a ceremonial event. Despite the parallel and sometimes politically charged nature of their pioneering work, the two men developed a warm personal friendship, united by the shared experience of bringing an entirely new form of propulsion to the world. They exchanged letters over the years and appeared at several joint events, at the Smithsonian, the Royal Aeronautical Society, and various university lectures. Both used their public appearances to push back against narratives that painted one as copying the other. Whittle appreciated von Ohain's honesty about having read his patent, but still arriving at a different design, and von Ohain admired Whittle's sheer persistence against Britain's penny-pinching establishment during his development years. While there isn't a huge volume of primary material, like a long correspondence archive, the friendship between the two men is well attested to in multiple credible sources and interviews, and it's one of those cases where the historical record is modest but consistent across all accounts. Both were as significant as the prototype jets that they helped bring into existence. Yet the irony is hard to miss. Whittle, who had to practically beg for every pound of funding, saw his Gloster E-28/39 lead directly to the development of the Meteor, Britain's first operational jet fighter. Meanwhile, Ohain, who had the backing of Ernst Heinkel from the start, produced the Heinkel 178, a truly pioneering machine, but one that is mostly forgotten, and if it is remembered, it's remembered mostly as a museum piece that no longer exists. Aviation history is full of such ironies, and this one is particularly sharp. Of course, the tale of the Gloster prototype is every bit as tumultuous and important as that of the Heinkel 178, but that, my friends, as you always know, will be a story for another day. As always, thank you all so much for watching, and a big thank you, of course, to the Patreon supporters. Yes, it has finally happened. I'm actually going to put a bit more focus on jet aircraft. But before people get out the pitchforks, fear not, piston-powered aircraft will not be neglected either. I'm going to try and strike some sort of a balance here. I don't know what that balance is going to look like yet, but all I can promise is that there will be videos in the future featuring aircraft that are powered by jet engines. A big thank you, of course, to our Wing Commander tier patrons, our highest tier supporters, and a warm welcome to Joe, who is the newest member of this special group. Now, I'm hoping to line up another live stream soon. There was meant to be one this week, but I was unexpectedly away from the office for a couple of days. I'll put up a notification on YouTube a few days in advance to try and give you all as much notice as possible. The topic will, hopefully, be related to this video and Ohain's engine. But that is all for now, as my voice is now slowly failing. Thank you all so much for your continued support, and I will catch you all next time. Goodbye.